Well, another paper that you commented on thinking about whether it would be published or not, although in this case the answer was simple, was the paper with Mills on gauge theories. Now, looking back from here, the time from your arrival to the time of that paper, which was 1954, if I remember right, is not so long from this perspective. Can you give some trace of how it developed, how it came to fruition?
I think I was very, very fortunate. I had earlier referred to the fact that the paper I wrote for my PhD thesis under Taylor was about using symmetry, the concept of symmetry, and group theory in mathematics to apply it to natural phenomena. For some reason, that was something that I already, when I was in China, was very much interested in. I was very fortunate that I got onto this track, or this particular aspect of the structure of physical laws that early. So when I was a graduate student in Chicago, beyond that paper that I just referred to about, which became my thesis, I studied the question of symmetry. And in particular, one important mathematical expression of symmetry was called gauge symmetry, or gauge invariance, which was invented by a great mathematician named Hermann Weyl in 1918. I was hooked on that idea. So as a graduate student, I scribbled some notes. And these notes I found a few years ago in my papers. And so they have now been republished. If you read those notes, you see that I was trying to say maybe this gauge symmetry idea could be used to generate a theory of how these elementary particles would interact with each other, what forces they exert on each other. So that key idea I already had. But to implement that, I got stuck. So I would work on it for a few days and abandon it. But then after 2 years, there were more elementary particles found. There were more desire to study how they relate to each other, how they interact with each other. So I would come back to this idea and then got stuck again with the implementation. This took place several times until 1953, 54. In 53, I was already at the Institute for Advanced Studies for several years, and the Brookhaven National Laboratory had a new, the world's largest accelerator at that time called Cosmotron, just beginning to operate. They want to get some young theorists to help the experimentalists there. So they asked me to visit Brookhaven for 1 year, 53 to 54, which I did. And they assigned a small office for me, and they assigned the office mate, and that turned out to be Bob Mills. Bob Mills was some 4 or 5 years younger than I, and he was just about to get his PhD, and he got a job as a sort of a pre-PhD postdoc at Brookhaven. So we shared the office. And of course, we began to talk about the various aspects of physics. I found him to be very intelligent and with wide-ranging interests. So naturally, we began to discuss this unfinished idea about how to use gauge symmetry to create interactions between particles. And then we got stuck at the same place. When Bob and I, years later, recalled, we were both vague about what precisely happened. But we said, apparently, that the reason that it doesn't work is because a fundamental formula which we copied from Maxwell may need some amendment. So let's add a term to it and see what happens. We added a quadratic term. At the time we said, if the quadratic term still does not work, we'll add a cubic term. But fortunately, when we added the quadratic term, after a couple of days of calculation, not very long, today we can teach to the graduate students in 1 hour. We found that all the difficulties disappear. All these very complicated formula, which became longer and longer, all cancel each other out, so that we got very beautiful, compact equation. So we knew we got something. Then there was a long struggle because the idea was beautiful. The structure was very beautiful. But how do you compare that with experiments? And there was one major problem which we couldn't solve, namely, according to what we structured, it was a set of equations. It apparently gives 0 mass particles, lots of them. But there were no such 0 mass particles to be found. So that was a big obstacle. In fact, in February 1954, while Mills and I were still doing this, Oppenheimer, back in Princeton, heard about it. And also, Pauli was visiting Princeton, and Pauli was interested in the idea. So Oppenheimer called me up and said, Frank, why don't you come back to Princeton and give a seminar on what you're doing? So I did. And at the seminar, Pauli gave me a hard time because he was interested in it, and he also knew that the idea would produce massless particles which were not experimentally found. So he kept on raising this question. So I had described that experience in my selected papers. After that, for some 4 months, Mills and I tried to solve this problem. We couldn't. But we felt that the idea was very beautiful. So we wrote a paper. At the end of the paper, there was a paragraph discussing this particular question. Why are there massless particles? Why we apparently were creating a theory with massless particles which were not experimentally found. That section was very difficult to write because we didn't know what the solution was. But today, with hindsight, if you read that section, what it essentially says is that there cannot be massless particles. So there must be something in addition, which we do not know. So we ended the paragraph in that note. I think in retrospect, we were smarter in this case compared with Pauli, because Pauli confronted the same question, and he became discouraged, and he never published anything about it. At that time, the editor was Gouchmit. We sent in our paper for publication. No questions were really asked. He accepted it without any questions, so within 2 or 3 months, it was published. Of course, now it has become a very important paper because later on, there were additional ideas, very important ideas, called the symmetry breaking, which became very successful starting in the 1970s.